Welcome. In this lesson, we're going to learn how to use Riemann sums to estimate the area under a curve. We're going to learn how to relate this to the total distance traveled by an object, and we're also going to learn the definition of the definite integral. This lesson will be broken up into several smaller videos. Let's begin with a warm-up. Let's find the area bounded by a rectangle. Consider the region bounded on the Cartesian plane by y equals 3, x equals 5, the x and the y-axis. What is the area of this region? Before continuing, let's make a sketch. As you can see, I have sketched y equals 3 here. And let me remove this so it doesn't look like it's negative. So here's y equals 3. Here's x equals 5. This is my x-axis and the y-axis. So the region we're interested in is right here. What is the area of this region? This can be answered using basic algebra. This distance here is 5 units. This distance here is 3 units. So the area of a rectangle is base times height. So the area here is a base of 5 times a height of 3. So we end up with 15 units squared. And to be a little more thorough, I can actually just go ahead and write units. All right, let's look at part B. How far does a person moving at a consistent rate of 50 miles per hour travel after 5 hours? Well, let's recall distance traveled equals rate times time. And we want to know how far someone has traveled, so we want to know their distance. Well, we're given a rate here. Our rate is 50 miles per hour. So I'm going to go ahead and write 50 miles per hour. And we're told they traveled for 5 hours. So let's go ahead and multiply this to 5 hours. The units of hours cancel, and we end up with 5 times 50, which is 250 miles. So this person has traveled 250 miles. Part C. Let's make a sketch of the curve representing the rate traveled as a function of time. And more specifically, I want us to make a sketch of representing the rate traveled from this part, from part B. So let's make a sketch of the velocity curve v of t, and let's use this sketch to find the total distance traveled after 5 hours. Notice here I made this sketch. On our horizontal axis, we're tracking time in hours. On the vertical axis, we have rate in miles per hour, and this green line here is right at 50, and this is the velocity curve. And velocity is constant. That is, we're told they're driving at a consistent rate of 50 miles per hour. So at 1 hour, they're driving 50 miles per hour. At 2 hours, this person is still driving 50 miles per hour. And so on all the way to 5 hours where they're still driving at 50 miles per hour. So let's use this sketch to find the total distance traveled after 5 hours. Well, for part B, we already know what that amount is, that distance is. It's 250 miles. What do you notice about how this sketch here relates to this value? And as a hint, consider part A. We found the area of a rectangle in part A, but why did we do that? So if you notice, the area under this horizontal line corresponds to the distance traveled. This area is precisely 250 miles. So let's see how this works. Along our horizontal axis here we have 5 hours. Along our vertical axis here we have 50 miles per hour. And I'm going to swap these around for no reason other than I have them swapped on part B, and this will help them match up. So there we are. 50 miles per hour, 50 miles per hour, 5 hours, 5 hours. This is the exact same problem we've already done to get to 250 miles. So the area under this curve corresponds to the distance traveled. Let's take this a little further, and in order to do that, I'm going to make a little space. Yeah, I'll put this here. I want to make a different graph, and I'm going to make a graph of their position function. So as you can see here, I have an axis. On my vertical axis, I have miles traveled. And on my horizontal axis, I have time in hours. And let's go ahead and plot points for what this person is doing along their journey. So if they're traveling at a rate of 50 miles per hour, after 1 hour, how far have they traveled? If you said 50 miles, here you are correct. What about after 2 hours? How far has this person traveled after 2 hours? If you said 100, you're correct. Now pause this video and see if you can figure out where I should plot points for their distance traveled after 3, 4, and 5 hours. All right, your graph should look something like this. This is the position function, S. And what this tells us is the position of the person as time passes. So after, say, 3 hours, we know this person's position is at 150 miles. After 5 hours, we know their position is 250 miles. If you notice the slope of this line, what is the slope of this line? It is 50 over 1, 50 over 1. So the slope of this line is actually 50 miles per hour is our velocity function. So again, the slope of this line is 50 miles for every 1 hour, which is just 50 miles per hour. So the first derivative of this position function is equal to our velocity function. Let's go ahead and sum this up below. Notice that the area under the velocity curve can be used to find the distance traveled by a person or object. In the warm-up, the velocity was constant. So in this case, this person was traveling at a constant rate of 50 miles per hour. So the velocity curve looked like a horizontal line. So in order to tell how far they had traveled after 5 hours, we just found the area of this rectangle. That was super easy to do. What about when the velocity of a curve is not constant? So what if we have a curve that goes up and down all over the place instead of being this nice straight constant line? This topic will be explored further in the next video.